That would have been bad. Yeah. Because only 8 students are online plus 1, 2, 3, 4, 13. So there are 7 students who are probably going to wait for the recording. Okay. In case I forget it one of these days, just remind me, okay? Either here or online, just make sure that the recording is started. Okay. Because I promised it, otherwise it should be okay. All right, so next, let's see what happens if you make this even more crazy. Okay. If you have W as a function of X, Y, and Z, but there is no rule that these variables X, Y, and Z should not depend on more variables themselves, right? Could have X as a function of, say, U, V, T, Y as a function of U, V, T, and Z as a function of. You could have more variables if you want. Okay. Now that we are in multivariable calculus, there is no limit to how many variables you could have in each of these stages. So the question is now, how do we know the rate of change of W with respect to those external variables? Okay. So how can we find partial W with respect to partial U, partial W with respect to V, and partial W with respect to T? Now it's a multivariable problem. Okay. Earlier we had a multivariable single variable problem. Now it's a multivariable problem. The important thing is to not get scared with the number of variables. Okay. So just draw another tree diagram here. So W, you just need more space. Okay. So there are 3 branches coming out of W, X, Y, and Z. Each of these will have its own branches. So now the tree diagram makes more sense. So this will have U, V, T. And once you understand it for one of them, the rest should follow, right? Y depends on U, V, T, and Z depends on U, V. Okay, so it's a slightly bigger tree diagram, okay, but the idea here is to still write the derivatives along each branch and then multiply downward and add rightwards. So nothing has changed here. Okay. So the derivatives here would be W with respect to X, W with respect to Y, and W with respect to Z. So that's the same as what we had in the first case. The only difference here is that down for the second stage, you're going to have partial derivatives because you have a multivariable situation, right? So this is going to be X with respect to U, X with respect to V, and X with respect to T. And similarly, Y with respect to U, Y with respect to V, Y with respect to T, and the same for Z. So I'm going to write subscripts just to shorten my writing. Y with respect to U, Y with respect to V, Y with respect to T, and Z with U, Z with V, kind of running out of space here. Okay. So if you just focus on one of them, you will understand what you have to do for the rest of it. Okay. So for the partial derivative of W with respect to U, just focus on the U branch. Okay. On the U branches, actually. So W is going to U via 3 different branches, X branch, Y branch, and the Z branch, right? So multiply those two, multiply those two, and multiply those two. So W with X, W with Y, W with Z. Okay, those are the 3 branches. So just focus on one at a time. Okay. So the partial of W with respect to U would be W with respect to X, X with respect to U, plus W with respect to Y, Y with respect to U, plus W with respect to Z, v with respect to u. All we are doing is replacing the t in the previous case with u, right? That's all we are doing here, except that these are all partial derivatives because this is a multivariable function. So multiply downwards, add rightwards. So what is the cleverest way of finding w with respect to v? What changes? Yeah.
Like everywhere it says du, just change it to v.
Yeah, just change the u to v, right? So w with respect to v would be dw dx. I'm saying d for partial here. Dx dv. All I'm doing is changing u to v because I'm taking the v branch now. Plus w with respect to y, dy dv, plus w with respect to z, dz dv. So just make sure that everything is agreeing here. There's a v, 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 v. And it goes without saying, if you want w with respect to t, let's change the v to t. And so on. And this last one kind of looks like what you had here. Okay. W with respect to x, x with respect to t, y, y with respect to t, and with z, z with respect to t. The only difference being that it's a partial derivative there, full derivative here. All right, so it looks bulky because you're having 3 variables in each stage, but once you write it down, you're just adding terms, nothing else. Okay, so let's go to that worksheet and finish off this worksheet number 5, I want to say. Yeah. And let's do the first 2 problems. In the meantime, please, do you have any questions about any of these? So can you try the first one? So just got 2 variables. Okay, I don't want to make it too crazy. Worksheet 5, problem 1. Actually, you can cheat in this problem, but I won't do that. Y equal to question is just to find partial f with respect to u at a particular point, 0, 1. The reason I said that you could cheat is because you could just plug in x and y into this function and find partial derivatives. That kind of kills the purpose, so don't do that. Okay. Trying to show how chain rule works. I mean, there's nothing wrong if I just plug in this here and plug in that here and do some horrible chain rule, right? And could do it, but that's not the point. Right, so the U branch, okay, F to U via X and F to U via Y. Partial F with respect to X is just 1/2 X negative 1/2. X with respect to U would be cosine of U square plus V square times 2U. Partial of X with respect to U. F with respect to Y would be 2e to the 2y. And Y with respect to U, note that I've written those terms kind of backwards. Okay, V first. So Y with respect to U is nothing crazy, it's just 3. Almost there. Okay. We need to clean it up because right now we got a whole bunch of things going on. We got X, U, V, Y. Okay. You don't want all those variables in the same answer. So make sure that your answer is in terms of U and V at the end. Okay. So this X should be replaced by sine of U square plus V square, and Y should be replaced by this term, right? So you can do that after you plug in your values. Okay. So at the point UV equal to 0, 1, that is what is given to you. Try to make it easier to handle instead of plugging in a whole bunch of crazy things. Okay. So we have X equal to sine of U square plus V square, which is sine of 0 square plus 1 square, which is a sine of 1. And Y is cosine of root V plus 3U, and that's going to be cosine of the square root of 1 plus 3 times 0, and that's equal to cosine of 1. So if you plug in U equal to 0 into this term, actually this whole entire term is going to become 0. So actually we didn't have to do that. Because when you plug in at U equal to 0 and V equal to 1, the partial of F with respect to U would be that entire term times 0, that's a 0, plus 2 times e to the power of 2y, okay, y is cosine 1. So it's 2 e to the power of 2y times 3. Okay, so that's going to be 6 times e to the power of 2 cosine 1. Yep. Then, these are all in radians. We are doing calculus, so all these are radians there. No. No. I know those values are kind of ready to flip over. Yeah. Cosine 0 is 1, sine 0 is 0. Cosine 1, I have no idea what it is. It's pretty close to 1. But I'm not going to compute those things. Okay. But any questions about how the chain rule worked here? Just another routine exercise in partial derivatives. Any questions online? Okay, the second one, which is similar to the one we did yesterday in class. Okay. And this is the kind of examples I would expect you to know for tomorrow's quiz. You should be able to understand what is given to you, okay, and how to make use of that in the chain rule. So problem number 2. You're given, now we got back to 3 variables, okay, f of x, y, z. The gradient of f right now we have a full battery. So the gradient of f at the point -3, comma ln of 5, comma 1 is -3, 5, 2. So that is all we know about the function f. We don't know what the function actually is equal to, okay, and we don't care. And x of t is -3 e to the power of t, y of t is ln of t square plus 5, and z of t is cosine of t. So the question is to find df dt at t equal to 0. Yeah. Pretty sure all of you, based on yesterday's example, would know how to do this. Okay. Before you do that, let me ask you a question. Okay. Mainly to, let me see if people online are still there. Okay. Why do you think these things are given here? You're given the gradient of f at this weird looking point xyz. Okay. Does it matter, or is it just given there for fun? What do you think? Those are the partial derivatives. Okay, these are the partial derivatives. Okay. This is your partial f with respect to x. This is the partial of f with respect to y. So what you said is probably true for this part. Okay. This is partial fx. This is partial fy. This is partial fz. And okay, nothing wrong with that. Yes, these are the x, y, z values when t equal to 0. Okay. If you plug in t equal to 0 here, get -3, ln of 5, and cosine of 0, which is 1. Okay. So we need that precise set of values to do this problem. Otherwise, we cannot do this. So that's why we are given that gradient vector exactly at this point. Okay. So note that if I gave you the gradient of f at 1, 2, 3, then the problem is not doable because we don't have enough information. Okay. So we are given the gradient of f at t equal to 0, and that corresponds to x equal to -3, y equal to ln of 5, and z equal to cosine of 0, which is 1. That makes the problem kind of complete in terms of the information you need to do this. So that is my responsibility to give you the correct set of values. Okay. But apart from that, it's a pretty routine question. a smaller tree. And as one of you mentioned in the chat, these are the partial derivatives given from the gradient vector. So you just need to look and you will see it. So we are not really using these values anywhere. Okay. You just need to make sure that they are given to you at the right point. Except for that, we are not going to plug in those anywhere or make use of that. dx dt is, well, we are given those functions here. Dx dt is just -3 e to the power of t. And at t equal to 0, that is going to be -3. dy dt is the derivative of this function. It's going to be 1 over t squared plus 5 times the derivative of t squared plus 5, which is 2t. And at t equal to 0, this is just 0. And the derivative of z with respect to t is sine of t. Again, at t equal to 0, that is 0. So the only non-zero term is actually dx dt. So if you plug it in here, you have -3 times this -3 from here, and that makes it +9. Okay, that is your final answer. Because this is 0, nobody cares. This is 0, nobody cares. Is it going to be zeros in all the problems? No, it depends on each question. So don't expect first term to be non-zero, second zeros. That just depends on how these functions are set up here. All right. So up to there for tomorrow's quiz. Okay, so I don't expect any huge dramas here. Just read the question and do what is asked. Any questions on those two examples or anything that's the end of 2.4. So just focus on the chain rule. Okay, all the other rules are rather trivial. The product rule and quotient rule, there's nothing really conceptual in those things. Okay, so time for some hard concepts. Okay, so hi. Oh yes, please. Yes, please. Thank you.
You're welcome.
All right. So all of you know how to find partial derivatives. Okay, at this point we can just focus on trying to understand what some of these things mean in the context of multivariable functions. So that's what we're going to do today, section 2.5. We'll be using very easy functions. The focus is on okay, what do these things mean for a given function? Okay. Directional derivatives, and the gradient vector. So conceptually rich section, so please write your notes carefully so that you don't kind of copy things wrong and then try to understand it the wrong way. Okay. So far this is what we know. If you have a function f of x, y, the partial derivative fx is the rate of change of f with respect to x, keeping y fixed. Okay. When I say y is fixed, that means you are going along or parallel to the x-axis. Okay. That is the rate of change of f along that line. Partial fx. Similarly, when you say partial fy, you're keeping x constant. So in a way, you're going parallel to the y-axis. That is your fy. So the question is, what if you wanted to find the rate of change of f in some arbitrary direction? Okay. So suppose you are given a point here and you want to find how does f change in that direction, say northeast. So the question is, what is the rate of change of f at a point, say AB. This is f of xy at a point AB in an arbitrary direction, which is not parallel to the x-axis or to the y-axis. Okay. That's a reasonable question to ask because there is no need to stay always parallel to the axis. Okay. And you can see why we are kind of looking at the word directional derivative. We are looking at the derivative along a certain direction. Okay. So when you write this fx by keeping y fixed, okay, you're looking at this as fx times the unit vector I plus 0 times j. Okay, because it's only along the y-axis. Okay, there is nothing along the j-axis. So when you're just talking about fx, it's just your fx component along the x-axis, nothing along the y-axis. Okay. Similarly here, you have 0I plus fy j. So it's starting at the base level here, right? Yep.
Are we in R2 right now?
We are in R2, yep. Everything that I draw here in R2. Yep. That's why I can draw it like this, right? XY plane. But the function is in R3. So it depends on what you're asking. This is in R3. That's a surface, right? You're finding the partial derivative of this with respect to x and with respect to y. Okay. Only two partial derivatives. We don't have a third variable with respect to which it's going to change. You understand the difference? Yeah. So here we have two of these, okay. Fx along the I direction, Fy along the j direction. The question is, what if we had an arbitrary unit vector pair along which we want to find the same rate of change? Okay. So suppose u1, u2. So in this case, u1 is I and u2 is 0. And the second case, u1 is I and u2 is 0. Okay. So suppose u1, u2 is an arbitrary unit vector. Which could means it could be anywhere now. It doesn't have to be parallel to the x-axis or y-axis. Okay. All right. Then please pay attention to this next part here. Okay. The rate of change along this direction for our function f of xy, instantaneous rate of change. That is how you start with your calculus, right? Instantaneous rate of change at that point P A B. You have to be given a certain point from which you're going to start your motion. Okay. At the point P equal to AB, in the direction of this unit vector u1, u2. for that function f of xy is given by partial fx times u1 plus partial fy times u2. Okay, so it's easy if you look at how I started this. We had along the x-axis, which was fxi plus 0j. Okay. So this was your u1, and this is your u2. That is if you are parallel to the x-axis. The second one, you have 0i plus fy j, and that is parallel to the y-axis. Okay. In that case, also you had u1 and u2. These are unit vectors, okay, which means the length is 1. So in general, if you are going to change it to some arbitrary component here and here, okay, all you're doing is just replace the I and the j by u1 and u2. Okay. You can check it back. So check if u1 equal to I and u2 equal to 0, we still get the partial derivative with respect to x. That means you're parallel to the y-axis, parallel to x-axis, right? And if u1 equal to 0 and u2 equal to j, you get fyj. So those are two special cases. You are staying parallel to one of the axes. But if you're not, if you are in some arbitrary direction like that arrow that you pointed there, okay, then both components of the unit vector will contribute to the rate of change. The question is, why am I so religious about this unit vector? Why not just some vector? Does it make a difference? What do you think? Why am I just underlining that word unit over and over and over? Yeah.
Because we care about direction and we want to keep the magnitude of the vector.
Yes, so we are just trying to find the rate of change of f at a point in a certain direction. Okay, actually, the size of that vector is not going to or should not really change anything, right? We are worried about the function at the point in a certain direction. Okay, the direction is no longer parallel to the x-axis or y-axis; it's in some arbitrary direction. Okay. So the only thing we need to worry about is what is the function, what is the point, what is the direction. Okay. The size or the magnitude of this vector should not change the answer. Size of this vector must not affect your answer. So if that vector was 3, 2 or 5, 8 or 12, 15, okay, that shouldn't change the rate of change of f in that direction. So that's why we scale it down to a vector of length 1, so that the entire focus is on f, the point, and just the direction. So it's a key part of the process that you keep it as a unit vector, always. And if you observe closely, okay, at what I just wrote there, you can see that it's nothing but the dot product of two vectors. So you know that the gradient of f is vector whose components are partial fx and partial fy. And if you call u as a unit vector whose components are u1, u2, what I've written there is just a dot product of these two vectors. The dot product of the gradient of f dot u. This is from the first week of classes, of actually last week, right? The product of these two, fx times u1 plus fy times u2. This notation is more compact and more useful because now we can write it in any dimensions, whether it's in R3 or R4, if you have this notation here, you don't have to worry about how many components are there, right? Just need to keep on adding terms. So this is the new concept, the first of the new concepts you're learning today. So let's write it down. Directional derivative. So if just calculus 1, you would have just said derivative. Directional derivative is multivariable calculus along an arbitrary direction. So let f be a function. I don't care how many variables there are, okay, of n variables maybe. We'll be mostly doing 2 or 3, but sky is the limit, right? N variables, and let P be a point with n 1x, 2x, 3, 2x, n coordinates. Kind of blagging out on that word, coordinates. Let U be a unit vector, U equal to U1, U2, dot, Un be any unit vector. Please write this carefully. The word unit is important there because it looks like a vector, so that's okay. It's a unit vector. Then the directional derivative of f at the point P in the direction of U. Okay, so you need 3 pieces of information to do this. We need the function, we need a point, we need a vector. Okay. In calculus 1, you just need a function. Now we need a whole bunch of things. Denoted by capital D with respect to, or of f at the point P with respect to this vector U. Okay. It's a very bulky notation. Capital D for directional derivative of the function f at the point P in the direction of U. Okay. So it's an all-inclusive notation there, is equal to the dot product of f with U and it tells you the rate of change of f with respect to distance moving with the unit speed. This unit vector is telling you how fast it is moving. Okay. There's the instantaneous rate of change. If you watch the textbook videos, I think he keeps on saying IROC, instantaneous rate of change. Okay. Of f with respect to distance moving at unit speed. That unit speed is what is given here. It shouldn't matter how fast you're moving. It's telling you remember that the components of this vector are partial derivatives with respect to x, y, z, and so on, right? So it's the rate of change of f with respect to distance because that's the gradient moving at unit speed. So you'll see the question phrased in different ways. Find the directional derivative or find the rate of change of f with respect to distance moving at unit speed. Same thing. So this is the golden equation. We're going to kind of live with this equation for a while. So kind of box it, frame it, whatever you need it. Yeah. All right, let's do an example quickly. So in terms of computation, it's a very easy thing. Okay, it's difficult to understand what it means. To do it, if you know how to do dot product, it's a pretty easy thing to do. So example, let's just do one with two variables for now. Let f of xy equal to 2x square minus 3y square. Okay, told you I'm going to keep my functions very nice and easy from now on. Okay. And let p equal to 1, 1. And let v equal to 2, 3 be a vector. Okay. One thing you should observe here is this is not a unit vector. Okay. This is some vector. So that's part of the process here. Find the directional derivative of f at the point P in the direction of V. Direction of V. Okay, so what are the two things we need? We need the gradient vector at that point. We also need a unit vector in the direction of V. Okay, those are the only things we need here. The gradient f is the vector with partial derivatives as its components. It's a two variable function, so only two components. And that's going to be just 4x and negative 6y. And at the point 1, 1, it's going to be 4, negative 6. That is a vector. Okay. Sometimes students forget to convert that vector into a unit vector. That's the only thing you should be careful here. So V is 2, 3. So it's not a unit vector. And we learned on the very first day how to convert a random vector to a unit vector, divide by its magnitude. So U is 2 divided by the square root of 4 plus 9, 13. 3 divided by the square root of the same thing. That is a unit vector. So the directional derivative of the function f at the point 1, 1 in the direction of this unit vector u, okay, is the gradient of f at the point 1, 1 dot u. There's an easy way to kind of put all this hard work into no use if you do the following. Okay. 4, negative 6 dot 2 over root 13, 3 over root 13. So I'm copying my gradient from here. Okay, did all the hard work. I copied from here, and the next step you just spoil everything. So you multiply this, you write 8 over root 13, negative 18 over root 13. Then boom, everything just goes waste. What is wrong? Yes, so I'm seeing a hand here. Let me just come back to you. Anybody online, who wants to tell me why that is wrong, why that is absurd, even. You need to add. Okay, so all right, let me hear your answer now.
The directional derivative doesn't, or vector doesn't represent the directional derivative, it should be a number. So you should, or like when you take the dot product, you should just take the sum of those.
Okay, the dot product is a number. Okay, that is the long story short, right? Yeah. whatever you said before that is correct, that the derivative is a number, but the dot product is a number. Okay, so, and that is the answer I got from online crowd as well. So this is 8 over root 13 minus 18 over root 13. That's equal to negative 10 over root 13. Okay. There is one thing that I come down severely on, that is these kinds of mistakes. Okay, at this point, I've said this so many times. Don't write the dot product as a vector, it's a scalar. Okay. No mercy there. Okay. If you write 5 plus 6 equal to 56, I don't care, but no, I do. All right, any questions about that? I hope all of you agree with me on the scalar part. Yeah.
So like geometrically, what I'm still confused as to what the directional derivative looks like. Is it like, do we sort of rotate the plane such that like one of the axes aligns with the unit vector we're looking at?
Yes, now the axis is again aligned. It's a crazy thing now, right? Earlier we were staying either flat like this or vertical like this. Now you are standing like this and trying to see how the function is changing in that direction. So
Rotate it such that it's parallel to one of the two axes, right?
one of the two axes from there, the U1, U2. Our new axis would be now looking like this. That is not our typical way of imagining things because we stand upright. Okay. Now we are standing like this and trying to see.
Right, but it's still oriented in such a way that it either looks vertical or horizontal, right? Like the unit vector.
Yes, one at a time.
Oh,
Yeah, okay. Not the whole thing. Yes. All right, any other questions on this? Okay, now let's try to do some surgeries on this thing. Okay. The reason why we spent all that time last week on dot product is because it helps us understand some deep meanings about this thing here. Okay. This is a directional derivative of f at the point P in some direction. But we know from last week, what do we know from last week? Well, that the directional derivative at f at the point P can be written as the magnitude of the directional derivative, magnitude of the gradient vector times the magnitude of the unit vector times cosine theta. Okay. Do you remember this? I don't see a response. Did I just write something completely new or is it familiar? Maybe this will look familiar. U dot V equal to magnitude of U times magnitude of V times cosine theta. Does that look familiar? That looks familiar. So if I have the dot product of these two, that also should look familiar. Okay. So there's two vectors, who cares? So we have two vectors like this. The gradient of f, let me just not do it. So the gradient of f like this, and some u like this. Okay. Now listen carefully about what we're going to do here. Okay. All of us hopefully know that the value of cosine theta never goes below -1 or above 1. Okay. So universal truth that cosine theta is bounded above by 1, below by -1. It comes from the unit circle, cannot go outside the circle. Okay. This happens when theta equal to 0. Sine of 0 is 1. This happens when theta equal to pi. Okay. Will come opposite. The theta is the angle between your direction and your gradient vector. Okay, this is the direction which you're trying to move, and this is the gradient vector. Okay. So point 1, cosine of theta is maximum. Okay, there is no higher value for cosine theta above this. Okay. At 1, when theta is equal to 0. Radians or degrees doesn't matter, but we are using radians here. Okay. When cosine of 0 is 1, okay, that is when this is a maximum. So at that point, or at that value of theta, this rate of change is the maximum value. Okay. What is the magnitude of u? Let me ask you that. What kind of a vector was u? I see some answers here, but what is the magnitude of u? 1. Do you agree? It's a unit vector. Okay. So this is 1. This is 1. If theta equal to 0, okay, cosine of 0 is 1. So the only thing we are left with is the gradient vector. The rate of change is maximum along the gradient vector. That's the only term remaining there, right? The magnitude of u is 1, cosine theta is 1. The only term remaining there is the gradient vector itself. So the direction of the rate of change is maximum along this, and the value of maximum rate of change is the magnitude of the gradient of f. This is a vector, that's a scalar. Okay. It's telling you that if you move in the direction of the gradient vector, you're going to increase at the fastest possible rate. Okay. This is a very important concept in applications. Okay. The gradient vector gives you direction of the fastest rate of increase, or rate of change. It's also called the direction of the steepest climb. If you're climbing a mountain, you need to go along the gradient vector. Okay. Steepest ascent or the steepest climb. Okay. So if you are at the foot of the mountain, and if you know how the mountain looks like as a function, okay, and if you climb every time you're going along the gradient vector at each point, you will hit the summit at the fastest possible rate. And the magnitude of this is the value of the fastest rate of change. The good thing is, if you know the gradient vector, these answers are fast, okay, because you just need to copy it down. Similarly, come to the other side. This is the gradient of f, and you are going opposite to this, so which means the angle is pi. At 0, you're along the gradient vector. Okay. Now you're going opposite to it. So this means u and the gradient are in the same direction. Now we are opposite. So 0.2 cosine of theta is the minimum at theta equal to pi. Okay, that is the least value you could obtain, and that is equal to -1. And the rate of change is minimum because of this. When u and the gradient of vector are in mutually opposite directions. So instead of going up, you're climbing down opposite to the gradient vector, you're just going down the fastest. Okay. So u and gradient vector are in opposite directions. In other words, the negative of the gradient of f is the direction of the steepest descent. In other words, you are the summit of a mountain, you want to come down fastest, just go along the gradient vector, okay, you will reach the foot at the fastest possible rate. Descent means you're coming down. The only difference between 1 and 2 is that one is along the gradient vector, this is opposite to the gradient vector, same gradient vector. Okay. And the negative of the magnitude of this gives you the value of the steepest descent. So coming down the fastest. What happens if you move perpendicular to the gradient vector? You're climbing the mountain, okay. This one says that you're going to reach summit the fastest. This one says you're coming to the foot of the mountain the fastest. Okay. What happens if you move like this at 90 degrees? What is the rate of change? What happens if you plug in theta equal to 90 degrees in there? What is cosine of 90? 0, right? So if you want to reach the peak and if you go in this direction, are you ever going to reach there? No. Okay. So the rate of change is 0 if you are going perpendicular to the gradient vector. The rate of change is 0. If theta equal to pi over 2, which means instead of moving along the gradient or opposite to the gradient, if you are moving perpendicular to the gradient, then nothing is going to change. Okay, you're just going to stay where you are. So I know there's a lot of things kind of written out. Okay, so the key things are the direction of the gradient is the steepest ascent. Opposite to that, or negative of the gradient vector, is the steepest descent. Okay, both of them are vectors, so these are directions. If you take the magnitudes, they give you the corresponding values of the maximum rate of change, increasing or decreasing. And if you are not changing, that means you are moving perpendicular to the gradient, okay, which is a concept which is more important later on, not right now. So these questions are very wordy, okay, but if you understand what you're doing, it takes only 1 minute to do it mathematically, okay, because all you need to know is what is the gradient vector for that function. Okay. So let's do an example. Any questions about this? All right, let's look at this. Suppose the temperature distribution along a plate is given by T of x, y, z. equal to 80 minus x square minus y square minus z square. Let's just keep it easier. Just d of x y would do. So that way I can tell a story about it. And insect is at a point one one. Okay, that is x equal to 1, y equal to 1. In what direction written as a unit vector should this insect move to cool off as fast as possible? So we're going to assume that this insect is pretty good at vector calculus, okay, for the time being. So in what direction as a unit vector should the insect move to cool off as fast as possible? I'm hoping that that's what it wants to do, okay, to cool off as fast as possible. And what is the magnitude or what is the value of the rate of cooling? Of the fastest rate of cooling. So it's a wordy problem, as I said. So you need to understand that we are trying to decrease as fast as possible. Okay, that is what it means by saying it's going to cool off as fast as possible means the temperature should decrease in whatever direction we are moving as fast as possible. Okay. And that will happen if you move opposite to the gradient vector. If you move in the direction of the gradient vector, you're going to get hotter and hotter. Okay, so cool off as fast as possible along the negative of the gradient vector at that point 1 1. Okay. That's because that is when the vector u and the vector gradient of t are in the same direction, right? What is the gradient of t? Can you tell me what the gradient vector is? Yeah. Oh, you're plugging in the values, right? So negative 2x and negative 2y, and then at x equal to 1, y equal to 1, that is negative 2, negative 2. Okay. That is the gradient of the temperature. Okay, that's the rate of change of temperature with respect to distance along the plate. Okay. So this here is the direction in which the insect should move if it wants to get hotter and hotter, right? Go opposite to it. To cool off, we need to go negative of the gradient of T, and that's going to be negative of these two, that's going to be 2, 2. So that's the only thing you need to keep in mind. If it was going to heat up, we'll go in the same direction. To cool down, go in the opposite direction. The question also says as a unit vector, so you have to divide this by the magnitude of this. Because the direction of a vector is always given as a unit vector. Okay. So the unit vector corresponding to this would be negative gradient of t divided by the magnitude of the gradient of t. And that's going to be the square root of 2 square plus 2 square. So the square root of 8. Okay. That's 2 divided by the square root of 8. I already applied the negative there. That is my negated gradient vector divided by the magnitude. And what is the fastest rate of cooling here? Can you tell me, just by looking at what I've done so far, what will be the answer for what is the fastest rate of cooling? It's somewhere here. Yeah. Negative root 8. The fastest rate of cooling. Again, it's decreasing. Okay. There's the negative of the magnitude of the gradient, and that is equal to negative root 8. In this case, the units would be in degrees Celsius per meter, whatever the units of temperature and distance would be. Is it clear as to what these questions mean? So it's asking for the gradient and its magnitude. It's positive or along the gradient if it is the fastest rate of increase, and it's going to be negative which is the fastest rate of decrease, okay, because of how the dot product works. Now, can you take that worksheet number 5 and do that problem, which kind of looks lengthy because I put a lot of things in there, but I think if you just do one thing, others should follow one by one. So this is worksheet number 5, question number 3. It's got like a million parts in it, but don't worry. Do you have a copy of that here? Do you want me to write it down? P is 1 to negative 1. V is 1, negative 1, 2. The first question is just asking you to find a unit vector for V, so that should be easy. Yeah. Let me know if I'm making any mistakes. So I have the gradient vector equal to 2, -12, -4 at the point P. Is that okay? And this is my unit vector. So the directional derivative of f at the point P in the direction of u is the dot product of these two. And I think I already told you it's a number. So just multiply and add them. So it's going to be 2 plus 12, 14, 14 minus 8, 6 divided by root 6, and that's equal to root 6. It's a number. Need not be a clean number, but it's a number. Everybody okay with part B? Any questions? The directional derivative of f is the dot product of the gradient vector with the unit vector there, right? And finding the dot product would be just multiplying the components. So it's going to be 2 plus 12 minus 8. And then the square root of 6 in the denominator is still there. Component y, yeah. And that's equal to square root of 6 over, or 6 over square root of 6. Yeah. Any other questions about part B? Just view of this one. Okay. Part C is asking you for the direction as a unit vector along which f is increasing most rapidly. All talking about the same point, so you don't have to recalculate anything. So f increases at the maximum rate or most rapidly along, what is the answer? Can somebody online tell me what the answer for part C would be? The gradient vector, the positive gradient vector, right? So it's certain there are 2, -12, -4. The question is asking you for the same thing as a unit vector, so you have to divide by the magnitude. Okay. It will be useful later, so this is not going waste anywhere. And this will be the square root of 144, 148 plus 16, 164. Good. And then part D is asking you for the value of the maximum rate of change. Okay. That will be just the positive magnitude of the gradient vector which you already found here. So in both these cases, you are moving in the direction of the gradient, okay, or theta equal to 0. What is different in E and F? Well, it's a small change now. Yeah. Just negate it, right? So it's going to decrease the fastest in the opposite direction to this. Okay. So it's going to be the negative of 2, negative 12, negative 4 divided by the square root of 164. And this will be the negative square root of 164. Okay, that's the only difference between the direction of the fastest rate of growth and the direction in which you are decreasing the fastest. Okay. I don't know what the main word for the opposite of growth would be, but fastest rate of decrease. Or this is the steepest ascent, steepest descent. Value of the steepest ascent, value of the steepest descent. So getting the gradient vector is the big thing, right? Everything is just following from it one by one. The last part is a little bit weird, okay, but that weirdness will kind of make sense in the next section. The direction in which f remains constant. What is the direction? Yeah. Kind of, but in terms of what we have done, what would be that direction where there is no change? When it is at 90 degrees, okay, so the dot product is equal to 0. Or when theta equal to pi over 2. That is when the direction derivative is equal to 0. Okay, that is what I mean by saying that does not change. Okay. Now the answer to this is going to look a little different, okay, because you know the gradient of f, which is 2, negative 12, negative 4. Okay. We don't know this one. We are trying to find this u. Okay. Let's call it as u1, u2, u3. So what you said is right, it's a plane, okay, but that plane is kind of arbitrary at this point. Only thing we know is that the dot product of these two is equal to 0. You know how to find the dot product. You have 2u1 minus 12u2 minus 4u3 equal to 0. How many solutions are there for this equation? How many u1, u2, u3? There are infinitely many solutions, including u1, u2, u3 being equal to 0. Okay. So any triplet u1, u2, u3 that satisfies this equation is a possible direction. Any u1, u2, u3. In R2, I would have called it an ordered pair. This is an ordered triplet, okay. u1, u2, u3, such that this equation is true, satisfying this. Is an answer. So you won't see a definite unique solution to this part, okay, because there are so many of them, right? Yeah.
So would it be incorrect to give this the equation of a plane that like any vector point on that plane would be?
That is right. Yeah. When you write it down, actually it comes out equation of a plane, right, through the origin. So this u1, u2, u3 are the three components, right? So you're essentially writing the equation of a plane in R3. Yeah. But it passes through the origin. So when you do your homework, you might find this part a little annoying because the answer looks a bit clunky. Okay? But all the other parts are pretty standard. Gradient, magnitude, negative gradient, negative magnitude. Okay? It's a repetitive process. So that is the thing about 2.5. Okay? Any questions about this concept here? It's a little weird when you do this because you don't see things like this in Calc 1. Okay. It's a lot more conceptual here, but let me know if you have any questions about what we did. Anything that was not clear in that. I know the dot product kind of magically came into it and changed everything. All right, so let's look at a very special case of this. Okay, we are not done talking about the gradient vector. It's such a very powerful thing. So section 2.7, we don't do 2.6 in case you're wondering. Level sets and gradient vector. This. Okay, so a little bit of a strange concept. Okay, we try to make it as easy as possible here. Remember that we started with a function like this, okay, z equal to f of x y, which is a surface in R3. So for example, if you have z equal to x square plus y square, you have a surface that looks like this. And all of us went through this process of trying to understand what it looks like. So what we would do is we take a cross section of this. So we take a knife and cut it parallel to the xy plane, and you generate a circle there. You take another plane here. You take another circle here. Okay, that's what you see if you look from the top. So if you set z equal to k, you have x square plus y square equal to k for some value of k being greater than or equal to 0. This generates a set of concentric circles on the xy plane. So it looks like this. So k equal to 0 is a point, k equal to 1, k equal to 2, k equal to 3, and so on. These circles are actually curves in R2. This is a surface in R3. These are curves in R2. Okay. These curves are called the level curves. These are also called the contours or the shadow of that surface on the xy plane. Okay. Or the contour of x square plus y square on the xy plane. So the new word here, or new words here, level curve. Level curve is the projection or the curve that you get, or the set of curves that you generate by reducing the dimension of z equal to f of xy by 1. So z equal to k for z equal to f of xy generates the level curves for f. Where do we see this applied, this level curves? If you kind of have been observant enough so far, okay, there is a very easy place to see this every day almost. Where is that applied? Yes, I know it's something that you see every day, and then yeah. It's something more scientific than that. A little bit, So, have you watched the weather reports? What do you see there when they show the temperature of a certain region? What do they show there? Radar, but how do they represent it, on the map? So for example, I'm just going to draw, this is the United States. Sorry about that. So you've probably seen curves that go like this. Okay, on a typical day, there'll be more curves like this, but you have these curves with 70, 80, 90, 92, 95. What do those curves mean?
It was like lines where the temperature is constant.
Yes, these curves are the curves where the temperature is a constant. Okay, look at what we did there. Those curves are the curves where the function is a constant. Okay, so what it's doing is you're taking the temperature T of xy and setting that equal to those values 70, 80, 90. Okay, so these are actually level curves of the surface T of xy. 70 and so on. Okay, there's a name for this. These are called isotherms. Okay. Iso means same, it's related to temperature. So isotherms show. So if you are standing here, for example, it means that the temperature is between 70 and 80. Okay. You might see pockets like this in between. So this is 72 or 85. Okay. So usually the map is more complicated, but on that curve, the function is the same. Okay, that is what level curves mean. Why do they do this? They could do instead a function of x and y. Okay. Imagine you wake up in the morning, listen to the news, say that T of xy today is this function. I don't think people want to hear that. They would rather see this picture. Okay. So they are doing that work behind the scene. And you can also draw similar pictures for the pressure at a certain point. What do you call these? You know, ISO. Surprised that nobody has heard these names. ISO bars. No. People also use it when they're climbing mountains. Okay, if you look at the topographical map, you will see things like this for the altitude of a certain region. Okay, so this is near to the summit, and this is outward of the. So this is what you call as a topographical map. Okay. So in all these cases, what is common is that the function is equal to a constant along that particular curve. Okay. That is the golden rule here. Temperature is a constant, pressure is a constant, height is a constant. Okay. So along a level curve, f of xy equal to a constant. The directional derivative at any point should be equal to 0 because it's a constant. Understand that? Since the function is a constant, the derivative is equal to 0. It's one of the first things you learn in calculus, which means that the gradient vector dotted with u is equal to 0 at that point on this level curve. The constant has 0 derivative, and by definition of our directional derivative, the dot product is equal to 0. Whenever the dot product is equal to 0, what is the angle between those two vectors? 90 degrees. Okay. So this means that the gradient vector is at 90 degrees, or it's perpendicular to the level curve of f at the point P. So not only does it tell you the direction of the fastest rate of increase or decrease, okay, for a given level curve, which means when the function is constant, it's also telling you that the gradient is perpendicular to the level curve at each point. So we'll make use of this to get some nice results tomorrow. Okay, that's what our agenda would be. And then depending on how much time we have, we will do other things. All right, so let me stop there. So tomorrow's quiz will be at just step to 1.4 plus 1.3, which is on tangent plane linear approximation. Okay. You should, of course, know how to find partial derivatives. That's a skill that is assumed at this point. All right, then I'll see you tomorrow. And I have office hours at 12:10 if you have any questions. Thank you.